All right, so I want to begin with just a little bit of a visual of what we discussed at the end of last time. Right, so we're talking about structure formation, how under what circumstances inhomogeneities will either just oscillate or whether they'll grow under gravity. Okay, so we found this wave number, the Jeans wave number, last time. Okay, given in terms of the background density, G Newton, and the sound speed. And we said that for wave numbers bigger than k genes, it just oscillates, basically sound waves. And for k less than k genes, the perturbations grow under gravity. Okay, and relatedly, we could define the gene's wavelength as just 2 pi over k genes. So here, of course, we could just say lambda less than lambda genes or lambda greater than lambda genes, small versus long wavelengths. Let's see. Okay, so let's say I just have some initial conditions. Here's the density perturbation versus position. And I've just summed up a bunch of modes with different wave numbers, a discrete set of modes. And we've just random Fourier coefficients. So you just get some mess as an initial condition. So that's delta, and implicitly there's an initial condition for delta dot as well in the code. Okay, so that specifies the system. And then we just evolve it under that differential equation we derived last time. Or for each mode, we can just evolve under the solution that we found. And I've set things up. It's not clear the way I've written it, but so that it makes it a little easier to see what's going on, I've chosen amongst my modes only one wavelength to be in this category, just a little bit bigger than lambda genes. And most of the modes are in that category. So you'll mainly see oscillations, but there should be a lurking instability in the system. Okay. Good. So these just look like sound waves of a messy state. And you can notice the longest wavelength in the system is starting to become more and more prominent over time. So that's just gravitational instability in this system. Okay, and this mode is actually growing exponentially. It doesn't look super fast, but I've chosen k to be almost k genes, so the corresponding frequency is not that big. There you go. If I highlight for you the single long wavelength mode in the system, highlighted in orange, you can see what it's doing. And just a reminder, the corresponding frequency from last time, we could write as CS k squared minus k gene squared. Okay, or maybe we could put absolute value here. Okay, so whenever you're in this category, this is the frequency of oscillation. If it's an instability, this is the coefficient in the exponent, e to the omega t. Okay, so this is how we should expect the system to evolve. If I were to, as I said, I've made things so that the one instability in the system has a k only slightly less than k genes, so the growth rate was relatively small. That's why you mainly saw oscillations and this slow instability. That was just me being artificial. There's no particular reason we should have those as our initial conditions. So I could easily change the initial conditions so that the gravitational instability would be more pronounced. If I crank up the background density, rho bar, I change things accordingly. All right, so it's already exploded. Okay, so we can easily have rapid instability on a similar time scale, let's say, to the frequencies of the oscillation. One doesn't need to be quicker or faster, quicker or slower than the other. So any questions about this? Okay, so again, you can imagine, therefore, that at late times, we really only care about the growing modes. Whatever's stable doesn't do very much. We can almost ignore that. Basically completely dominated by gravity at late times, and we just have to know whether those modes exist. Are there modes that have k less than k genes? If they're in the system, they can completely dominate at late times. And if for some reason all the modes are in this category, well, that's a relatively boring system, and we just should bear that in mind. All right, any questions? All right. All right, so now the main task for today's class is to worry about the fact that we did not include expansion in our analysis last time. We attempted, formally we tried to expand around a background that was homogeneous, but we also declared it to be static. And because of gravity, that thing doesn't exist. The gravity will make the background dynamical, as we know. So we have to expand around the self-consistent background. And so that's actually a bit of work to do. So unfortunately, this is going to take us some time, but maybe it's worth it. So let me remind you of the equations we wrote down last time. We have the continuity equation. Again, density field or mass density and velocity field. Then the Euler equation. Okay, we have forces from pressure and gravity. And then finally, the Poisson equation. Now, these equations as written, this is at the nonlinear level. I haven't expanded around any background. So as long as I can trust the Newtonian physics, so for the matter in the universe, these equations should still be true. I haven't deleted expansion. I just haven't written it in a way that makes it clear how we're going to separate out the expanding part, the background part, and the perturbation. So that's the next step. Okay, but is everyone okay? All right, so as we've done throughout the whole course, usually the optimal strategy to handle background is to switch from physical coordinates to co-moving coordinates. So that's going to be our task. We really have to just rewrite these in co-moving coordinates. Okay. Now, as we've done in the course, usually when I write a co-moving coordinate, right, I write x. That's already the co-moving position. And here last time, our position was x. Okay, so now what we want to make explicit is that X that was there was the physical position all along. Okay, we were just doing Newtonian physics. We weren't going to some fancy coordinate system. They were good old physical coordinates is what we've been using all along. And funnily enough, we want to move to a different coordinate system, the co-moving ones. Okay, and I'd like to reserve the notation X for co-moving as we've always done. And usually when I write physical, I write X sub phys, phys, but I don't want to write phys a million times, so I'm going to just write that as X sub p. That will be the physical position. Okay, so that means I should go back here, and implicitly, there are physical positions that are relevant, because every time I take a gradient, if I write a gradient, this you could think of as d dx. So I want to be explicit. These will have always been physical distances, so physical derivatives. Okay, so I can write a p subscript here, and so forth. So that would mean, so if I write grad sub p, I mean d dx with respect to the physical coordinate. Okay? And then I have to think about this velocity. Okay, so over here, what I want to use, like we've done, I want to use the so-called peculiar velocity. Which, like everyone does, they just call that thing v without a p subscript. It's okay, because my p subscripts means the full physical stuff. Okay, so v physical, right, which I'm going to write as v sub p. The physical velocity means, well, it means d dt of x physical, nothing too fancy. And then the only thing we need to remember is the relationship between physical and co-moving, right? So we need to remember x physical is ax, as we've said many times. Okay, so let's write this, the physical velocity of the total system out. So this is d dt. We've done this step once or twice in the course, ax. And so I take these derivatives. So I get a dot x plus a x dot. And this is a nice separation. This is a separation between really the background contribution, right? This just is related to the fact that the universe is expanding. So we could call this the background piece if we like. And I could write that as v bar if I like. And the fact that it's proportional to x is just tells you the reminder that the stuff that's further away is moving faster. This is just the background homogeneous expansion of the universe. And then we have a new term, which is x dot. If everything were homogeneous and isotropic, you know, everything is frozen in co-moving coordinates. X dot would be 0. So the fact that I'm allowing for an x dot is because I'm allowing for peculiar motion, relative motion to the background expansion. Okay, so this is the perturbation, if you like. All right, this one, a dot, I'm going to rewrite that as h times a, because I can. And this thing here, we just call that our velocity. So we're going to write this as hax plus v. Okay, so anyway, I'm just separating out the total velocity of the system, the background velocity plus a relative velocity that we're interested in, a small perturbation. Delta V would be a good name, but nobody in the literature calls it delta V. They just write V. It's understood. It's relative to the background. Is that okay? Good. So please, any questions? All right, so now we have to have a little fun with partial derivatives. Oh, so actually, let me highlight something. So again, everything was physical. So if I'm going to put little p subscripts on my position, I need to put p subscripts on my velocities. Everything was a physical velocity of the system. So I need to put a p here and wherever else you see them. Is that it? Yeah. Is that okay? This should be clear, right? Everything was totally physical. Now we're doing the funny thing of moving to co-moving because it will help us separate out expansion from perturbation. Okay, so let's talk about a change of coordinates. So we started with our physical position, xp. These are coordinates, tell us where we are in space-time, and time t. And I want to move to co-moving coordinates, x and time t. And the mapping is just that our new coordinate x is the physical over the scale factor. Okay? And we're not touching time, so I guess I could just write t equals t. So we're moving from these coordinates to those coordinates. All right. Now, at the risk of sounding being a bit redundant, when you have an old set of coordinates and you move to a new set of coordinates, it helps, at least for me, when I do the partial derivatives, to give all the coordinates different names. Okay, so that t, sorry, that's going to become t prime, and the new coordinate we'll call that t. Is that all right? So the mapping here is t equals t prime. So even though we're not touching time, it will help us perhaps to give them different labels, as you'll see. So over here, even though this is regular time, I'm going to put primes on our old coordinates. Is there another t somewhere? I guess that's it. Is that all right? So I'll make that clearer. All right. So let's see. I'd like a bit more room. So xp over t, over a, sorry. T is t prime. Okay, so our task is to just change coordinates. So here, for example, I have to take gradients and rewrite a gradient with respect to a physical position as a gradient with respect to co-moving. So grad p, or we can think of that as ddxp. How can I write this in terms of new coordinates? What's a general expression that takes us from old to new? Forget this for 1 minute, then we'll plug that in. What's a general expression that takes us from a ddx? Now I want to take derivatives with respect to these x's and t's. So multivariable chain rule. Right, so I don't want ddxp, I want like ddx. That's one of our new coordinates. And I also have a ddt, I shouldn't leave that one behind. Okay, so I want stuff like this. So what should I put here? What's this prefactor? But not even looking at the blue, just what's a general rule if you go from old to new? Yeah. dx physical, right? So these x's here, and then the thing you start with, dx dp. And then this prefactor, just prefactor. Sorry, say again. dt prime. Not quite. Remember, we want ddx, so the x is going to appear there somewhere. So what would the chain rule tell you? dt dxp. Okay, if you want ddx and you want to go to new coordinates, just write ddx, and then just write out the sum of the new coordinates. dx dx, dt dt. It doesn't matter that I called them x's and t's, right? It could go a, b, c, d, right, and so forth. So that's the multivariable chain rule. And now I want to use the blue. Now I got to figure out these prefactors using this information up here. Okay, so dx dxp you see, is just 1 over a. So that's no problem. D dx. And what about dt dxp? What's dt dxp? Sorry? 1 over physical velocity. Well, let's just stare at the blue. What does the blue tell us? That's the actual mapping from old to new. dt dxp. Well, t is, you see, t doesn't depend on xp, right? We're going from these coordinates to these ones. So it depends on t prime, but not xp. So therefore, this is 0. Is that all right? Okay, so this is our mapping. So if you were to stare at sort of if we were being lazy, and we just stared at the denominator here, and someone says, what should I write as ddxp? I might just say, well, I don't know, xp is ax, so maybe I should just write ax. But you see, that's too quick, because why is the a in front of the derivative? But this is the correct answer, right? If you do it properly. So if you were just guessing, you may not know if the a should be out there or in there. What do you do? Right, so we have this. Or equivalently, I can write this as the gradient of the p variable as 1 over a, the gradient of the x variable. And usually we'll end up writing 1 over a grad. In other words, it will be understood that when we see a gradient, we mean with respect to our standard x variable. Is that right? So up here, the gradients are going to be super simple. Wherever we see a gradient, you just replace it by a 1 over a. Okay, now we have to do the time derivative. Okay, so we have ddt primes. This is where you have to be careful with the chain rule. Okay, you would be forgiven for saying that since t equals t prime, ddt prime equals ddt. But that is not so. So let's write out what ddt prime is. Yeah. I mean partial ddt prime. Sorry, can you repeat?
Yeah, I thought you were talking about the total.
Let's write out the partial derivative. That one has a surprise too. Let's write out the partial derivative. So we don't think, we just use multivariable chain rule. So I have to write ddx, right? And then a ddt. And then the prefactor here by the chain rule is dx dt prime. And then this one is dt dt prime. Is that okay? Multivariable chain rule. And I'm just implicitly acting on something. I can put an f here for a function f, right? We're always implicitly acting on some function. Okay, so this one here, all right, dx dt prime, well, the a can depend on time, or t prime. So I have to remember that there's an a sitting there. So the first term here, I can write that xp is a different coordinate, so that's xp. And then I can write ddt prime acting on 1 over a. A good old scale factor is a function of time, so we have to remember that. And then ddx. And then dt prime, well, that's 1. So we get ddt. Maybe I want to keep these equations, so I'll erase here. All right, we have the derivative of 1 over a. So this prefactor here, xp minus a. Okay, you get a minus from the derivative, a dot over a squared. Dots mean time derivatives for me, all right? And then you see you can pull out one of these a's, I can put it there, and the other a, I can put it there. And xp over a is little x. And then Hubble. So that's that prefactor. So let us summarize. We just learned that d dt prime is minus x h d dx plus d dt prime, d dt. Okay, or if we prefer gradients, we can write this d dx here as grad. Does everyone believe that? Okay, so let's flesh out what we're doing here. Right, this equation at first sight looks nuts because t equals t prime. So how could d dt prime be anything other than d dt? But there's a correction. Okay, there's maybe the fun and games you might find if you, I don't know, in thermodynamics when you do all these partial derivatives and things get confusing. Okay, what are the words we would wrap around? Why is it possible that d dt prime is different than d dt? How is that possible? And I'm not lying when I say t equals t prime. Let's think, these are partial derivatives. When you do a partial derivative, what does that mean? Here I'm differentiating with respect to t prime at fixed something. What am I fixing? What am I fixing? Space, and space, which x? One of the x's. Which am I fixing? That's right. Yeah, that's what we mean whenever I write these derivatives. We were fixing its partner. Okay, so implicitly this means at fixed xp. That's how we understand all these derivatives here. Right? I'm fixing its partner. And this one, I'm going to the new coordinates. I'm fixing its partner, which is x. At fixed x. And this one means fixed t. Okay? So since xp and x are different things, they were related by a scale factor that depends on time, we can have the possibility that d dt prime at fixed physical is different than d dt at fixed x. And they do differ by an amount that depends on the expansion, the time dependence of A. Okay, so we have these pair of equations. Well, this one, so I don't know, A and B. And we have to plug those into this thing. All right. So we get through a bit of pain today, and then there's the payoff on, on Wednesday once we do all this funny partial derivative stuff. But any questions about this? All right. So let's start with, I don't know, the easiest one perhaps, which is the Poisson. So Poisson doesn't have any time derivatives. So all we have to remember is that every time you have a gradient in co-moving, you just marry it to a factor of 1 over A. Right, so we have two factors of A here from the Laplacian. So 1 over A squared. We'll call that equation 1. Now we'll try the continuity equation. Okay, the left-hand side, d rho dt prime. By this rule, I'm going to write it as d rho dt. That's that piece. And then this correction. All right, that's just the left-hand side. Well, sorry, I wrote the left-hand side. I mean, this is just, I mean, the first term in the continuity equation looks like that. And this equation, I don't know, let's put this on the board somewhere. We'll probably need it. The physical velocity is a background piece plus a perturbation. All right, and then I have to write out this. Grad P, rho V. So the grad just gives me a 1 over A. That bit's easy. Acting on rho. And now I want to replace it by this velocity. Background plus perturbation. All right. So let's add these two things and set it to 0. Okay, so in the divergence here, first I can take the divergence of rho V. And then I need to take the divergence of this other stuff. So, all right, so first of all, I could take the gradient or the divergence here of rho and multiply it by that thing. And then finally, I can take the divergence acting on this thing. Is everyone okay with that? All right. So there's something nice. This thing cancels this thing. And the final term I get, this is some divergence acting on this, I have div x. What's div x? The divergence of x. Anyone know? Little math question. What's the divergence of the vector x? 1? It could be. In 1 dimension, that would be right. What if we're in 3 dimensions? Div x. 0? Based on the philosophy that 50% of my answers are 0. The divergence of x is not 0. It's a vector that goes out. It looks like it diverges. Yeah. Is it 3? Yeah, it is 3. Right? You get a partial derivative with respect to x coordinate plus the partial derivative of the y plus the partial derivative of the z. 1 plus 1 plus 1, we get 3. Okay. So this thing here is 3. The a's cancel. All right. All right, so altogether, we get d rho dt. Maybe I'll write this one next. We get plus 3h rho plus the divergence rho v. Okay, we'll call that equation 2. Any questions about this? All right, so the standard form of the continuity equation at the end of the day, not too shocking, the gradient, right, or the divergence gets married to a 1 over a, but then we pick up this extra piece as well from the change of variables associated with time. So now this equation here, with its 3h rho, let's check that this makes sense on the background. The background we know is just a boring old FRW expanding universe. So it has to recover what we know on the background. Otherwise, this can't possibly be right. So the way we've set things up on the background, I mean, rho equals rho bar, which can depend on time, right? In expanding universe, densities can depend on time, but they don't depend on space. That's the background. And then remember, V is like the peculiar velocity. So on the background, V is 0. Everything is just caught up in exactly the Hubble flow. Questions about that? Everyone clear that's what we mean by the background? Right, V was the relative velocity compared to the background. So now this equation says d rho background dt plus 3h rho background equals 0. And does this thing look familiar? Okay, earlier on the course, we derived from general relativity d rho bar dt plus 3h rho bar plus the pressure. But this material is slowly moving stuff. So its background pressure can be ignored. And so this is gone, and we're left with that. And the solution of this equation, d dt rho plus 3h rho bar, right, we're not going to go through it again, but you can check that has solution rho bar proportional to 1 over a cubed. Okay, so this is just the familiar statement that matter redshifts like 1 over a cubed as the universe expands. Okay, good. Now we have to finally rewrite this one in co-moving. So it's slightly more painful. Let's try to write this thing out. Okay, I'll write out the left-hand side. Rho. It's going to be a big mess. Okay, my ddt prime, I need to write this down. That's the time derivative. Oh, no one caught this. I should not have written a v there. In my notation, I have ddt acting on v. I don't need to write it again with the brackets, but anyway, I'm going to stick to this notation where I have a big brackets. This whole stuff is going to act on some v. I mean, may as well write down that v from this rule up here. That v there. Peculiar velocity plus background velocity. And then I have to write down this stuff. Peculiar velocity plus background. Dotted into gradient. And gradient just gets married to a 1 over a. Okay, so that's the left-hand side of this thing. And then the right-hand side, we just have to put 1 over a's from the gradients, and we're done. Okay, any questions about that? Can anyone see any simplification? Anything that cancels? There's one term in this, there's something in this brackets that cancels. Yeah.
The H and the X.
Right. Yep. Yep, because these A's go away, and that thing is then the, oh yes, there's a minus sign, so that term cancels this term. Okay. I guess I can rewrite that. That second term. And I have no simplification for the right-hand side, so I'm just going to leave it like this. That's our Euler equation in co-moving coordinates. Okay, no approximations, other than the fact that we're Newtonian, but I haven't linearized or anything. We're just reorganizing the expression. All right. So this thing, we can check it on the background. Okay, so I'm going to again write rho equals some background function of time. Pressure can be some function of time. And V is 0. And the Newton potential, well, I just write it as some background Newton potential. That one I cannot declare is only a function of time. I will have to leave that as a general function. All right. So then if I come here, this left-hand side has a rho background. The V's are 0, so they go away. And I have to write d dt. And this is the background velocity. All right? Background, right? So d dt, I have to worry about this. There's an HA, and I can pull out the x. Because partial time derivatives don't act on x. They're independent coordinates. And then the right-hand side, well, p is a function of space only, so its gradient vanishes. And we should be careful about the Newton potential. I'll keep that. All right, so it looks like this. Rho bars we can cancel from both sides. HA is A dot, right? So this says A double dot. X is minus 1 over A grad phi. Squeeze it in here. I take the, if that's correct. Yeah, now I take the divergence of this equation. Right, so div x we know is 3. So I get 3A double dot minus 1 over A, the Laplacian of phi. And on the background, the Laplacian of phi is just 4 pi g rho bar. This is minus 4 pi g rho bar. And so this tells us A double dot over A minus 4 pi g over 3 rho bar. You may recognize that's the second Friedmann equation. Again, ignoring pressure on the background. Okay, so all these equations are consistent. Any questions about that? Okay, so this, again, these are just sanity checks. All right, so now the point of all this is to look at the perturbations. So we want to do first order perturbations on this system. So for density, we're going to write rho like before, rho background, which now remember can be a function of time, plus delta rho. But the notation we usually use is that people, well, I mentioned it last time, we might write delta rho, crazy notation, but delta is the perturbation delta rho, which is a number, divided by rho bar. Is that all right? That's the notation people use. All right, so delta is a number here, delta rho is a variable. Okay, so this is the density contrast. Right, so if delta is 0.01, literally just means there's a 1% deviation from homogeneity, the perturbation relative to the background. So this turns out to be a very nice variable to track around, a dimensionless measure of how far we've departed from homogeneity. And so up here, I'm just going to write this as, we write this as rho bar brackets 1 plus delta. Okay, and to be sure, rho bar can depend on time. Our perturbations can depend on space and time. Right. For pressure, we just write the background plus a perturbation. Not going to give that any particularly fancy name. And the Newton potential, again, the background plus a perturbation. Right? I don't need to write V because we already understand that V is the perturbation. Is everyone okay with this? All right, now remember, we've already checked that everything works at the background level. So any zeroth order equations, you just delete them. They're already satisfied. Only write down the first order perturbation. So for here, I just think the first order perturbation in phi is what we're calling delta phi. So over here, I should write delta rho. Right? But delta rho, just to be clear, delta rho is just rho background delta. So all right, this is rho bar delta. We can call that 1 prime. That's the first order perturbation in the Poisson equation. Let's move it up here. All right, and the next we want to do continuity. Did I delete the continuity equation? No, I didn't. It's up here. Okay, we want to write down this thing to first order. Okay, so first of all, I'm going to write ddt. And I just want the perturbation, the first order perturbation, which we're writing as rho bar times delta. Plus 3h delta rho, which is rho bar delta. And then the last term, 1 over a divergence of, rho bar v. Okay, so who can tell me? In this term here, I didn't bother with delta rho. I only wrote rho bar. Why did I do that? Right? Should I be adding a v times delta rho or something to that term? I'm not doing that. The divergence of which? No, the delta rho, this is a function of space and time. The perturbations, just generic functions of space. So they can have all sorts of derivatives. Their divergence can be non-zero. And you see what I did here? I just replaced rho by rho bar and pulled it out because rho bar is a constant, so it comes in front of the derivative. And I didn't bother with a delta rho. But why didn't I bother with delta rho in this term? This is at the heart of what we're doing. First order perturbations. So with that, I want to work to first order, right? V is small. That's the idea, right? Remember, V is already the perturbation. You can think of it as delta V. So the V is already the small perturbation on top of the background. That means this term is already first order. That means I can multiply by 0th order in rho, the background, to make the whole thing just the first order piece. Those are the tricks that we have to use. Otherwise, we're just going to be rewriting the full equations again. Okay, now I want to do a little bit of simplification here. I can take a time derivative of rho bar times delta, rho bar, well, time derivative delta or delta dot, it doesn't matter. And then I just rewrite the rest. Okay, and then there's this piece here and this piece here. Right, they both multiply delta. So can you tell me something about the sum of these? What are the sum of the two blue terms? Yeah, why should it be 0? I mean, other than the philosophy that half my answers are 0, but right. Yeah. Yeah. So on the background continuity equation, these two terms cancel. Okay, and then we can, on the remaining thing, we can divide throughout by a common factor of rho bar. So we get this relatively nice equation, delta dot, well, let's just write equals minus 1 over A div V. Okay, so first order, if you know your density field, let's say, and its time derivative, the divergence of the velocity has to match that. Or if you set up initial conditions, let's say you tell me delta and you tell me V, the velocity field initially, then the corresponding time derivative of delta is just locked in by this equation. You just take a divergence of your initial velocity field. All right, so we'll call that one 2 prime. And then we have one more linear equation to write down, which is somehow the first order perturbation in this thing. We game to do that one on the board. I guess we came this far. All right, so now number 3, or the Euler equation, we have to perturb this thing to first order. All right, so now we do have to be a bit more careful. So first of all, the row on the left, I can treat that thing at 0th order, and then I have to grab everything here at first order. And then we have to worry about a first order in delta rho and grab anything here that's 0th order. Those are the two terms that would be first order. So let's first put rho on the background. And then we can grab everything at first order. All right, so dv dt is first order because V is first order. And then this bit that involves V here, if I act on the background, that will be first order by the V. We can have that acting on that. Now we have V dot grad Hx. Questions about that? There's also ddt, you see, acting on this. That's 0th order. ddt, that's background. So do we agree that if you put rho on the background, those are all the first order pieces? Okay, so then I want to write delta rho. I can move that to first order, which is also known as rho bar times delta. And then I could multiply that by the zeroth order part of this thing, which means I have to act ddt on the background. That's the only zeroth order piece. Pull the x out because, well, anyway, it acts only on things that are functions of time. All right. So fun again with derivatives. Now we have to know, right, this gradient doesn't act on Hubble. That's a function of time. I can pull the h here. So this acts on x. So anyone want to tell me what is v dot grad acting on x? V dot grad acting on x. Right? The point is we can do that, right? Because we know we have the explicit function of space, which is just the function x. So we can do the derivative. And v will come for the ride somehow. V is the thing we're solving for. So we're not going to solve for v, but we know how grad acts on x. So that one may or may not be so obvious. Maybe half an hour ago, someone would have said, I know the answer, that's so simple. And now I've scared you all into being worried as to what the answer might be. Go, yeah. VV, good guess. But unfortunately, it's not 3V. We're really contracting the derivative here with this one. We're not contracting with x. So if it was div x, it would be 3. Maybe we can write it out. So this thing here is the thing on the left here. This is Vx ddx, Vy ddy, Vz ddz, and then acts on x. Yeah, I guess I can write that as acting on or multiplying x, y, z. Okay. So you see Vx ddx only acts on the x. So that gives you a 1 that multiplies Vx. So we act on the first component, it maps it to Vx. And when you act this on the second component, only this one acts. And so it leaves you with a Vy and a Vz. So it equals V. Okay, there's no 3. All right. And let's see, the right-hand side of this thing. Can I just write that? This stuff's in the road now. So I'm going to write this as HV. Okay, can I erase that bit so I have some space? All right, and then the right-hand side, I have to write out this stuff. So the perturbation in pressure, that's no problem. That's right. I just write delta P. And then the gravitational term, again, I have to be careful because I can write background times perturbation or perturbation times background. Looks like this. So it's a bit of a mess. HA, remember, is A dot. So this whole thing is just A double dot. And, well, I took a divergent. Here it is. We still have this equation here. Statement about the background. Grad phi is related to A double dot up to a factor of x. Acceleration is related to the gradient of the potential. Okay, so that's nice. Because this term here with the acceleration and this term here, therefore cancel. All right, so let's just summarize what we have. We'll divide throughout by this rho bar. I'm left with uv dt Okay, so that's our set of, hopefully they're all on the board, yes. 1, 2, 3 prime, the first order perturbation equations. Any questions about this? All right, so the strategy with these things now, we can use the same strategy we used last time. You just want to somehow combine them into a single equation. Okay, so I won't write it all out, but let's just state, you can take the divergence of this thing, the d dt dv. Okay, and now it's all set up to be simplified. Okay, I don't think I'll write out every step on the board, but you can probably see what's going to happen, right? Wherever you see you have a div v here and here, you just use the perturbed continuity equation. We're going to eliminate velocity in favor of the density fluctuation, density contrast delta. So you just replace div v by minus a delta dot. Okay, so basically here you're going to get some delta double dot and a single delta dot. Good, and then here we're going to use, as we did last time, delta p, we're going to say is the sound speed squared delta rho, or cs squared rho bar delta. Okay, so that's how we can relate the pressure perturbation to density perturbation from last time. And then here, we just have the Poisson equation. So we use 1 prime to eliminate the Laplacian acting on delta phi, again in terms of delta perturbation. So you just substitute them in. That's all. Right, I can just maybe write that answer on the board. So this is our primary equation after all this pain. We'll have to say insert and a tiny bit of simplification, and we end up with this. Is that all right? I guess this 2 here is a 2. It's not like the 3h that is in the background density perturbation. This one ends up being 2. Okay, you can already see there's a 1h from that piece. But here, where you insert ddt acting on div v, that means, the div v can also be written as minus a, like this. So when you do the insertion there, you see not only will you get a second time derivative of delta, which I've pulled out the front, you will also get a time derivative acting on a, and a dot, which is proportional to Hubble. So you'll get this type of HV term twice, and you end up with the 2h. So that's the only little step you have to do to go from there to there. The questions about this? Yeah.
Why are we allowed to do delta dot if delta can be a function of spacing?
Yeah, just because I'm using that as my notation. So I don't mean anything deep by that. So I'm literally just, you're talking about straight ordinary versus partial? Yeah, so sorry, when I write delta dot, it's just a shorthand notation. Okay, maybe I shouldn't use it, but often people just get a bit lazy and write this. So I'm just using that as my notation. Is that all right? But yes, by all means, I can write out partials here if you prefer. Is that okay? I don't wish to confuse things. I don't know. In the literature, people just love putting dots. So somehow it has to be understood that it means partials in this context. All right. So basically, through that hard work, right, from last time when we ignored the expansion. Well, we certainly didn't have that term, Hubble coming from expansion. And we had this exact same structure here, but without the a squared in the denominator. Okay, so again, it's not too shocking that you should marry your derivatives to a factor of a. So the fact that you get a 1 over a squared there from the two derivatives is pretty simple. That's what you would guess. But in some sense, this painful hard work is just to get out this 2h delta dot, which you may not have guessed. And given our 3s and our 1s and our so on, well, that one's a 2. And when we solve these equations, that 2 matters. Okay, it's not, sometimes in this business, maybe you've seen in this course, we can sometimes be cavalier and use order of magnitude estimates. Sometimes that's not good enough. A 2 in a differential equation like this matters a lot. If it was a 3 or a 1, that would have very, very different kinds of solutions, funnily enough, as we'll see. All right. So again, we can Fourier transform this thing. From delta, which remember, these things are functions of space and time, to delta of k and time. And in the literature, people often just call this thing, I don't know, delta sub k. So if I do the Fourier transform, we're just going to get, yeah, now I write out partial derivatives since I want to put a hat on my Fourier transform. And then as before, minus Laplacian, right? We do a Fourier transform minus Laplacian gets mapped to k squared. Let's organize the last 2 terms inside of our brackets as we did before. Okay, so this is quite nice. So our density perturbation, the full one at first order in K space just obeys this relatively nice second order ODE. Okay, so we can call this a linear density perturbation equation. So any questions about this? Now, just a quick comment on the K's as they appear, right? So, oh yeah, so when I Fourier transform, we're just using K is the partner of X. So if X is co-moving, this would be called the co-moving wave number. Okay, so just as we're going to think of, X is just a label of where you are in your space-time, where you are in space. It doesn't move in space per se, it's just a point in space. So if you, just as before, if you have 2 things, let's say one is here and one is here at the fixed X, in the actual expanding universe, their physical distance separates. X physical, which is AX, will change. Similarly here, right, we're going to talk about co-moving K, or K vector, which is the partner of the co-moving X. So this also means that if let's say I took a wave, if we are in a situation where this term dominates and we get wave solutions yet again, if I have some wave like this, a particular mode, it will have the property that by construction, its K is fixed. It's a fixed K. K is not a function of time, okay? But the actual wave will have its physical wavelength, right? So let's think about that. So just as physical is xp is ax, in momentum space, the physical one, we call it k physical, is k over a. It's inverted. As you can see here, right? The physical wave number, you would write cs squared k physical squared. So this you could write, if you like, cs squared k physical squared. And so that means over time, what does this predict? If k is fixed, just as x is fixed, the physical wave number is decreasing in time. That's the 1 over a. The physical wave number is going down, means the physical wavelength is growing. And we could also just say, maybe in terms of wavelength, it's even more obvious. We can talk about lambda, 2 pi over k, and lambda physical, 2 pi over k physical. This tells you that lambda physical is a lambda, right? Physical wavelengths are just stretching as the physical wave numbers decrease. So over time, this mode here may become something like this. Is that all right? So k physical decreases with expansion. Okay. But often we just talk about the co-moving wave number k is somehow this mode that's frozen in our mind, even though it's actually expanding. Okay, we'll have to use that language as we go forward. Anyway, this ODE is something that we can solve, at least in certain limits, and we will do that on Wednesday. Okay, so thank you.